Alright guys, in this section we're going to be discussing multiple angle and product to sum formulas. In the previous section we introduced sum and difference identities, and we're going to use those formulas to derive more trigonometric identities. We're going to have four major categories. The first one will involve functions with multiple angles. Then we'll have identities that involve squares of trigonometric functions. Third category would use half angles, and then we'll have product to sum and also sum to product formulas. So we're going to start with multiple angles here, and the first type that we'll see would be the double angle identities. If we have sine of 2u, and we're trying to figure out how to evaluate something like this, we can think of sine of 2u as sine of u plus u. From here we can use the formulas from the previous section, our sine of a sum. So we can use sine of the first one times the cosine of the second one plus sine of the second one times cosine of the first one. But in this case, the first angle and the second angle, they're both the same. So we have sine of u cosine of u plus sine of u times cosine of u, which is the same term. So we put it together into and have 2 sine of u times cosine of u. In the same way, we're going to see how cosine of the double angle, cosine of 2u, can be written as cosine of u plus u. And then from there, we can use our cosine of a sum formula from the previous section and get a new identity. Again, using my sum formula here from before, I get that cosine of the double angle is equal to cosine squared of u minus sine squared of u. Now, it so happens that I can use my Pythagorean identity and rewrite or have a couple of different variations for this cosine of the double angle. So remember your Pythagorean identity, sine squared plus cosine squared is equal to 1. So if I replace this cosine squared with 1 minus sine squared of u and combine it with the negative sine squared of u, I get that the cosine of the double angle is also equal to 1 minus 2 sine squared of u. And here we have another variation of this cosine of the double angle. In the same way, if I replace sine squared of u with 1 minus cosine squared of u and combine it with the cosine squared of u that you already had, I will get that the cosine of the double angle is also equal to 2 cosine squared of u minus 1. So here, notice how the equation in green and the equation in black here gives you 2 different variations for the cosine of the double angle. And we're going to use those interchangeably depending on what we need in our problem. Now for tangent, we have that tangent of u plus u is equal to tangent of u plus tangent of u. All of that divided by 1 minus tangent of u times tangent of u. And of course we can simplify this into 2 times tangent of u divided by 1 minus tangent squared of u. And there we have our new set of identities there. Now of course we're only doing the first 3 because you can do the other 3 just like we did in the previous section. You can always find the other 3 as reciprocals of the first 3. So if you know how to find the first 3, then you can always use the reciprocal identities to figure out the other ones. Now in this example here, we're asked to solve cosine 2x plus cosine of x is equal to 0. And I can't do anything with cosine of 2x and cosine of x because they have different angles. So here's where I'm going to get to use my double angle identity. So, and remember we had 3 variations for cosine of 2u. So I'm going to purposely pick the second one here. If you look at the identities that I have here, 2 cosine squared of u minus 1, because that would leave me everything in terms of a cosine. And so by doing that, I get 2 cosine squared of x plus cosine x minus 1, all of that equal to 0. That's a quadratic in cosine. So I factored it, and we've done already enough practice with this. And once you factor the left side, you set each factor equal to 0, and then you solve for cosine of x. So we're going to have the cosine of x is equal to 1/2 cosine of x is equal to -1, and then you're done with the algebra. From here you use your trigonometry. All of these values are from the inner circle, so when is cosine 1/2? It's positive on the first and fourth quadrant, so that would be pi thirds and 5 pi thirds. Now remember, because we're not giving an interval here, we're finding all the solutions, so we gotta add the 2 pi n to both solutions here, and we still have to do cosine of x equal to -1, and that happens at pi. Okay, and again, since we're finding all the solutions, we're going to have pi plus 2 pi n. All right, so here's another example where we're given some conditions about the angle theta, and we're asked to find, in this case, the sine of the double angle, cosine of the double angle, and tangent of the double angle. All right, so I'm going to use what's given here. They tell me that sine of theta is 3/5, and theta is in the first quadrant, so that's going to make everything easy in terms of sine because everything is positive in the first quadrant. But it's very important that you know where theta is in case you need to add a negative to one of those three functions here. So I'm going to start with sine of the double angle. I'll use my identity that we just derived. Sine of 2 theta is equal to 2 sine of theta times cosine of theta. And then from my triangle here, I can figure out what sine of theta was given, but cosine of theta would be adjacent over hypotenuse, which is 4/5. The rest is just simplifying or calculating this and leaving it in an exact form. We have a 24/25. Okay, in the same way, we'll do cosine of the double angle. And we had 3 variations for cosine. You can use either one, since you can figure out any of the trig functions with the right triangle in here. I'm just going to use the one that has sine squared because I'm already given sine, so no need to do extra work here. 1 minus sine of theta is 3/5, but we're going to square that, right? And remember, you're multiplying by 2 as well because it's 1 minus 2 sine squared of theta. Okay, so we end up with 1 minus 2 times 9/25. 2 times 9 is 18/25, and we have our answer would be 7/25. In the same way, we're going to find tangent of 2 theta. We use our formula for the tangent of the double angle. 2 times tangent of theta over 1 minus tangent square of theta. Okay, so tangent of theta from our triangle is 3/4. So we just start plugging everything in here. Once we have the right identity, the rest is pretty straightforward. It's plugging in the values that we have or that we found, and then we just evaluate. Simplify it as much as we can. Okay, after a little bit of working here, we get the tangent of 2 theta is equal to 24/7. All right, so here's another example, and we want to rewrite cosine of 3x in terms of cosine of x. So we're going to have to use not only our double angle identities, but also our sum and difference. If you think of cosine of 3x as cosine of 2x plus x, I can use my cosine of a sum identity, and within that process, we're going to have to use the double angle identity for cosine. We want to end up with an expression in terms of cosine of x only. So we start with our sum, cosine of a sum identity, and that's cosine of 2x times cosine of x minus sine of 2x times sine of x. For cosine of 2x, we go ahead and use our double angle identity, and since we want everything in terms of cosine, we purposely choose that variation of the cosine of the double angle. 2 times cosine square of x minus 1. All of that is being multiplied by cosine of x. I use my sine of a double angle identity, which is 2 times sine of x times cosine of x. And all of that is multiplied by sine of x. From here, I'm going to distribute some things, combine some terms in here, and see what we have. So distributing the cosine of x, we get 2 cosine cube of x minus cosine of x minus 2 sine square, because sine times sine is sine squared times cosine of x. All right, I still need to take care of this sine square of x because I want everything in terms of cosine of x. And the only thing that comes to mind here is Pythagorean identity. Remember, sine squared plus cosine squared is equal to 1. So we can use that identity to rewrite this sine squared as 1 minus cosine squared of x. And all that is times cosine of x. Now I have everything in terms of cosine of x. The rest is just simplifying and rearranging the terms, cleaning it up a little bit. Okay, we go ahead and distribute the 2 and the cosine of x, and we get those terms in here. And finally, I can combine some like terms. So 2 cosine cube of x plus 2 cosine cube of x is 4 cosine cube of x minus 3 cosine of x. All right, for the next set of identities, we have the power reducing formulas. And these formulas are going to be derived from the previous ones that we've seen. And actually, we're only going to need the cosine of the double angle. So if you recall what we just finished doing, cosine of 2u is equal to 1 minus 2 sine squared of u. And this was one of those variations. Well, if we take this identity and solve for sine square of u, we're going to get one of our power reducing formulas. So again, solving for sine square of u, we move the cosine of 2u to the other side, divide by 2, and then get this identity. It's called power reducing because we're going from sine square, exponent 2, to an expression that has exponent 1. Right? So we're reducing the power, hence the name here, power reducing. Similarly, we're going to take the other variation of cosine of the double angle, which is equal to 2 cosine squared of u minus 1. Take that and solve for cosine squared of u, just like we did on the other one. But instead of sine squared, we're going to solve for cosine squared of u. Similar procedure, and we get our cosine squared of u is equal to 1 plus cosine of the double angle over 2. There it is. Those are power reducing formulas. Now, for tangent, we're just going to use our quotient rule that says tangent is sine over cosine. Since it's square, it would be sine square over cosine square. Use the 2 identities that we just derived and put one over the other one. And notice how the denominators are going to cancel out, the 2's in there. And we end up with just 1 minus cosine of 2u over 1 plus cosine of 2u. And there we have our power reducing formulas. Again, you can always find the other 3 by taking the reciprocal of this first 3. So here we have an example. And notice we have our identities here on the side, on the right. So we're going to have to rewrite tangent to the 4th of x in terms of first powers of cosines of multiple angles. First thing we want to do here is rewrite tangent to the 4th as tangent square of x square, right? So we have, that's equivalent to tangent to the 4th power. And then we're going to use our identity here, our power reducing identity for tangent. We have it right there. And we just substitute that tangent square of x for our identity. Yeah, there was a little typo here with the letters, guys. I transitioned from x to the u. So our identities use the letter u, and the problem here is giving you an x. But it's the same thing. It's just a little typo there on the variable that we're using. Now we're taking all this this quotient here, and we're going to square it. And we can just square the top, the numerator, and square the denominator. So I'm going to go ahead and expand that, and that's what I'm doing now. And there we have it. That's the expanded version of it. Now, I still have to change some terms in here because we want the expression in terms of the first powers of cosine. And well, 1 is already is a constant, then we have cosine double angle, but then this terms at the end is our cosine square. We don't want anything but first powers of cosine, so we're gonna have to change those powers, and here we're gonna get to use power reducing formulas once again for cosine. Okay, so changing the cosine squared of du to 1 plus cosine 4u over 2. So notice how the angle on the cosine square is 2u, and when you use the identity you have to double that angle. So double of 2u would be 4u. So that's where that 4u comes from. And I'm doing that on the top and on the bottom. This will get a little messy, but you know, after we simplify, we should have a relatively nice expression. Okay, so what I'm doing now is trying to put everything on the numerator over 2 and do the same thing in the denominator, right? Just put everything under the denominator 2, and those 2's are going to cancel out, right? The denominator on the top and the denominator on the bottom, they will go away. Here we have it, and once they go away, I can combine a couple of things here on the top. The 2 plus 1 is 3, and that happens on the top and the bottom, and that's probably all I can do, right? We accomplished our goal of having an expression in terms of the first powers of cosine with multiple angles. Notice how we have cosine of 2u, cosine of 4u, the top and the bottom, but they're all to the first power, right? We don't have any squares or cubics or anything like that. So there we have it. All right, our next set of formulas are called half angle formulas. So just like we have double angle formulas, we're going to have half angle formulas. And as you may guess, these are going to be derived from the previous set. So the power reducing formulas got derived from the double angle of cosine, and now these half angle formulas are going to be derived from the power reducing formula. So recall what we just finished doing. Sine squared of u is equal to 1 minus cosine of 2u over 2. Okay, well, using that identity, what would sine squared of a half angle be? So instead of u, I'm going to replace that with u halves, or 1/2 u, whichever way you want to look at it. So sine squared of u halves, now remember u halves is your angle here, would be equal to 1 minus cosine of double the angle. But what is u halves times 2? Double that will be just u. So that's 1 minus cosine of u over 2. Once I do that, I'm going to take the square root on both sides. Since I don't want sine squared, I just want sine of the half angle. And when you take the square root on both sides, you always end up with plus or minus, right? We're going to have plus or minus square root of 1 minus cosine of u over 2. And there we have our first half angle identity. Similarly, for cosine squared, we're going to derive the cosine of a half angle from our power reducing formula. All right, it's going to work in the same way as the sine of the half angle, and it looks very similar to it as well. You can end up with plus or minus square root of 1 plus, instead of minus, it's plus cosine of u over 2. And there we have our cosine of a half angle. Now here, for the tangent, it's not as intuitive as the first two. It will require a little bit of work in verifying, so I've skipped that work, and I'm just giving you the identity here. Tangent of a half angle is 1 minus cosine of u over sine of u, and there's also another variation which is equal to sine of u over 1 plus cosine of u. Now it's worth noting here that the sign on the sine of half angle and cosine of half angle, the plus or minus, it's have to be one or the other. So that's going to be determined by the quadrant in which the half angle lies. Not the u, but the u halves. Here we have our identities, and also we have an example here where we're asked to find the exact value of cosine of 105 degrees. We could use, set it up as a half angle. Cosine of 105 degrees is the same thing as cosine of 210 over 2 degrees. Here we're going to get to use our half angle identity for cosine, and that says, okay, plus or minus, but it's going to be one or the other. And remember what we said, is depends on where the half angle is. The half angle is 105 degrees, and that is on the second quadrant, okay? Cosine is negative on the second quadrant, so then that's what's going to determine the sign here for our identity. So it'll be negative the square root of 1 plus cosine of u, which is 210 degrees, and all of that divided by 2. Notice how the purpose of setting it up this way, so that that u is in the unit circle, and then we're able to do it with exact values. Once again, this negative is there because 105 degrees is on the second quadrant. The 105 determines the sign, not the 210. So it's the quadrant of the half angle, not the other one. All right, so here we have the negative square root of 1 plus square root of 3 over 2, which is the cosine of 210 degrees. All of that, now remember that's negative because that's in the third quadrant. All of that divided by 2. Here we have it. Now the rest is just simplifying this, cleaning it up in a way that is more presentable. All right, what I'm going to do is put all the numerator here, all over 2. So I'm going to combine those two numbers. And we get 2 minus square root 3 over 2. All of that is being divided by 2. Once I combine the fraction over a fraction, we get 2 minus square root 3. 2 multiplies the other 2 there, so we get a 4 there on the denominator. And we can split the big radical here on the top and the bottom. So we end up with negative square root of 2 minus square root 3, all of that divided by square root of 4, which is 2. All right, so here we have an example of finding all the solutions on the following equation in the interval 0 to 2 pi. Okay, so we have cosine squared of x equal to sine squared of the half angle x over 2. And this will be a good opportunity to use our half angle identity. So sine of a half angle is plus or minus, right? Square root of 1 minus cosine of x over 2. And since we're doing sine squared, we're going to square that whole thing. So we don't have to worry about the plus or minus here, because when you square it, positive or negative, we end up with a positive quantity here. So we have cosine squared of x is equal to 1 minus cosine of x over 2. We cross multiply and end up with move everything to the left, have 0 on the right, end up with a quadratic in cosine, and this we know how to do, right? We just go ahead and factor so that we can set each factor equal to 0. So we get 2 cosine of x minus 1 equal to 0, cosine of x plus 1 equal to 0. From there, solve for cosine. We have cosine of x is equal to 1/2, and cosine of x is equal to negative 1. Right, since we only want the solutions from 0 to 2 pi, we just have to think about that one revolution. Right? When is cosine 1/2? That happens at pi thirds and 5 pi thirds, right? First and fourth quadrant. As a matter of fact, we already did a similar problem previously. And when is cosine negative 1? That happens at pi. And then we have our 3 answers. Now, one way that you can check this is by plugging this into your calculator. If you look at your original and just move one to the other side and plug it in, fix your window to, since we only want the solutions from 0 to pi, just fix your window to just see that x equal to 0 from 0 to 2 pi. And notice how it crosses or it touches the x-axis at 3 points. And those are our 3 solutions. You can also verify it by doing second trace, going to 0. And once you give it a left bound and a right bound there, it gives you the actual 0. And of course, it's a decimal. It's like 1.047 ... But if you calculate what pi thirds and 5 pi thirds is, all those will be your zeros. We also have pi as a 0. You can also do second trace to pi, and pi is 3.14, and there you have it. That's the 0 right there, right in the middle, pi. So this verifies the work that you've done here algebraically. All right, next set of identities are called product to sum formulas, and these formulas are going to be derived from the very first set that we did on the previous section, our sum and difference formulas. So if you recall, your sine of a sum is equal to sine of u cosine of v plus sine of v cosine of u. And also the difference, sine of a difference, is the same thing, but instead of a plus, we're going to have a minus. All right, so if we take these two identities and we add them, we get the following result. Sine of u plus v plus sine of u minus v is equal to, notice those two terms right there are the same. Sine of u, cosine of v, but one is positive, the other is negative, so they cancel each other out. So we end up with just 2 sine of u, cosine of v. Okay, now notice on the right side, I have a product. On the left side, I have a sum. All I have to do here is just switch the two sides and then divide everything by 2. So that 2 moves to the other side as a 1/2. And we end up with sine of u times cosine of v is equal to 1/2 the sum of those two signs. Right, sine of u plus v plus sine of u minus v. And there we have it. This is our first product to sum formula, where you have a product of a sine and a cosine, and you change it to a sum of two sines. So here we have the other 3 identities, product to sum identities, and they're derived in the same way. You just have to take different combinations, just like the way we did for sine. We could do it for cosine and derive the other ones too. We're going to use them here in the problem. They want us to rewrite the product sine of 5x times cosine of 3x as a sum or difference, right? Whichever one applies. So we have sine times cosine. That happens to be that third one here of our identities, and it's actually the one that we proved. Okay, rewriting it in here, our u would be our 5x, and our v would be the 3x, right? So then applying this into the formula, we're going to start, they all start with 1/2, and then we're going to multiply that by sine of the sum, right? U plus v. So that will be 5x plus 3x plus sine of the difference, 5x minus 3x. All right, so simplifying this a little bit, we get 1/2 sine of 8x plus 1/2 sine of 2x. And then we've accomplished what we wanted, is to write this as a sum, write this product as a sum. Right, our last set of identities here are going to be our sum to product formulas. And this is going to be the opposite of the previous ones. Instead of having a product to sum, we're going to have a sum to product. These identities are going to be more useful for us, especially when solving, because we typically want to have a product to be able to set each factor equal to 0 when we're solving trigonometric equations. These identities will be derived from our previous identities. So this is a little bit of readjustment. I'll prove one, and the other ones are going to be verified in a similar way. If you recall what we just did on the product to sum formulas, we have one of them, right? This is the one that we proved previously. If we let x, I'm going to relabel some variables here. If we let x be equal to u plus v and y equal to u minus v, then u would be equal to x plus y over 2, and v would be equal to x minus y over 2. Now you can verify this, right? So if you add u and v, you would get x. If you subtract v from u, you're going to get y. You can verify that yourself. Now substituting these variables in here into our product to sum identity, we get sine of x plus y over 2 times cosine of x minus y over 2 is equal to 1/2 sine of x plus sine of y. Remember? According to our relabeling here. All right, moving the 1/2 to the other side, we get 2 sine of x plus y over 2 times cosine of x minus y over 2 is equal to sine of x plus cosine of y. And we can switch the two sides here, but basically we're going from a sum, look at the right side of the equation, to a product on the left, right? And then we have our first sum to product identity. Now, the other ones are going to be proven in a similar way. For the sake of time, we're going to skip over those proofs and just give you the identities here. In this example, we want to find the exact value of sine of 195 degrees plus sine of 105 degrees. Now, you may say, well, I could use sum and difference formulas for each one and find it that way. Sure, but that would take you a lot longer. And since we already have this sum to product, applying one of these identities would not only save time, but it would also help us practice going from a sum to a product. Here we have it, and we're going to use the very first one here. we get that's equal to 2 times sine of the 195 plus 105 over 2 times cosine of 195 minus 105 over 2. And notice that once we clean that up a little bit, we end up with angles that are from the unit circle. 2 sine of 150 degrees times cosine of 45 degrees, and they're both from the unit circle, so we can find this answer, the exact answer value for this problem. Sine of 150 is 1/2. Cosine of 45 degrees is square root of 2 over 2. Cancel 2 out, and then the final answer is square root of 2 over 2. All right, so here's an example where we're really going to take advantage of our sum to product formula. So we have sine of 4x minus sine of 2x equal to 0, and we're asked to solve here. So I can't factor anything here because the angles are different. Right? You have 4x and 2x, so we're going to have to use some identities to be able to come up with a product here. So this is where the sum to product comes in handy. So I could take these two, use the right identity, and that is 2 cosine of the sum of the two angles over 2 times sine the difference of the two angles over 2. Right? And all of this is still equal to 0. Once we simplify, we're going to get 2 cosine of 4x plus 2x is 6x over 2 is 3x times sine of 4x minus 2x is 2x over 2 is just x equal to 0. Now the 2 in front just cancels out because we have 0 on the other side, so we can just divide everything by 2 and that 2 goes away. So we end up with a product here, and now we can set each factor equal to 0 and go from there. We set cosine of 3x equal to 0, and we have sine of x is equal to 0, right? And we've done this kind of problem already. When is cosine equal to 0? Our angle is 3x, so that happens at pi halves and 3 pi halves. But since they're pi apart and we're finding all the solutions, every pi we're going to have a solution. After we've found our angle here, we can just solve for x by dividing everything by 3. Right? And then x is equal to pi 6 plus pi thirds n. So that's part of our solution. On the other side, we have sine of x equal to 0, and sine is 0 at 0 and pi, and then it repeats every pi, right? 2 pi, 3 pi, and so forth. So our solution here is pi n, and there we have it. Now, if we were asked to find the solutions from 0 to 2 pi, you can use your general solution here to just list all the ones that fall in from 0 to 2 pi. I'm putting them in an order here, so I get 0, pi 6, pi halves, 5 pi 6, pi, 7 pi 6, 3 pi halves, and 11 pi 6. So those will be our solutions from 0 to 2 pi. Now remember, you can always verify this in your calculator or in some graphing utility. Writing your equation here, or the left side of the equation in your y equals, let the calculator graph it. Fix your window from 0 to pi, and notice how this graph intersects the x-axis at exactly 8 points, right? Which are the ones that we have there in green. So this is a great way to verify not only the amount of solutions that you have is correct, but also the actual solutions for your problem.